Readers block writers, writers block readers. That's the classic database trade-off, unless you use multi-version concurrency control. With MVCC, a reader never waits for a writer, ever. But that gift comes with a hidden cost. Your table silently bloats, and deleting rows won't reclaim a single byte. MVCC is the default concurrency model in Postgres, Oracle, and InnoDB. It's what makes them scream in write-heavy OLTP workloads. Imagine a hotel booking engine handling thousands of reservations a minute, while customer-facing queries constantly check room availability. Without MVCC, a booking update would stall every price check query. With MVCC, those reads just pick an older, consistent snapshot and carry on. To understand how, you need to look inside a tuple. In Postgres, every row version carries two hidden system columns, xmin and xmax. Xmin is the ID of the transaction that created this version. Xmax is the ID of the transaction that deleted it, or, if it's an update, the transaction that replaced it with a newer version. A live version has xmax either 0 or unset. When you update a row, Postgres does not modify the existing tuple. It inserts a brand new version with a fresh xmin. The old version stays right where it is, with its xmax set to the updating transaction's ID. A reader running at transaction ID 103 will see the snapshot defined by all committed transactions at that instant. Since version 2 was created by transaction 105, it's invisible to 103, so the reader happily sees version 1. The writer never waited, and the reader never waited. A delete works similarly. It finds the current live version, sets its xmax to the deleting transaction, and commits. The old data stays on disk. From the outside, you'd think the row is gone, but physically it's still there. It just became invisible to any snapshot newer than the delete. That's your first hint of bloat. All those superseded and deleted versions are dead tuples. They still live in the heap, and they still have index entries pointing to them. Nothing reclaims that space automatically. You must run vacuum. Vacuum scans the table, identifies dead tuples that are no longer visible to any active transaction, and marks that storage as reusable. Without it, your table grows and grows, even if you're deleting half the rows every hour. Here's where it gets painful. Vacuum can only remove dead tuples that are invisible to all active snapshots. If you have a long-running transaction, say a reporting query that takes 2 hours, it holds a snapshot from the start. Any dead tuple created after that point could still be needed by that old snapshot, so vacuum cannot touch it. Over 2 hours, a busy orders table can pile up millions of dead rows. When the report finally finishes, vacuum has a mountain to climb. A typical production scenario. An e-commerce orders table handles 50,000 updates a minute. A nightly analytics job runs for 3 hours, keeping a snapshot open. During that window, 9 million new tuple versions accumulate. The table jumps from 5 gigs to 22 gigs. All queries, even simple index scans, become slower because they must wade through extra dead tuples. Then auto vacuum kicks in and tries to clean up 17 gigs of dead data, hammering I/O for an hour. Let's trace it with concrete numbers. Start with one row, balance 100, created by transaction 500 and not yet deleted. Transaction 510 opens a read-only session and takes its snapshot. Now transaction 511 runs an update. It inserts a new version, balance 200, created by 511, and stamps the original as deleted by 511. When 510 reads the row, it still sees the old balance, 100, because 511 hasn't committed, and even if it had, 510's snapshot predates it. No locks, no waiting. You can spot this in the statistics tables. Look at the ratio of dead tuples to live tuples. If the dead count is 5 times the live count, every sequential scan is reading 5 times more data than necessary. Index scans still probe the dead index entries, degrading B-tree traversal. Indexes amplify the bloat. When you update a row, every index on the table gets a new entry pointing to the fresh tuple. The old entry stays, still pointing to the dead tuple. Over time, the index can become 30% or more dead weight. So both the heap and the indexes need vacuum attention, and the index cleanup can be even more expensive than the heap. Why not just use locks? In a locking system, an update holds an exclusive lock on the row, so readers must wait. That waiting can cascade under load. MVCC sidesteps that completely. Reads are never blocked and never block writes. The price is storage overhead and the need for garbage collection. So MVCC is a clear winner for mixed read-write workloads where you can't afford any blocking. But if your workload is append only or you rarely update, the locking model is simpler and avoids vacuum entirely. The production lesson is straightforward. Monitor dead tuple counts aggressively. In Postgres, set auto-vacuum to run more often than the default. Lower the scale factor so it triggers before dead tuples exceed 20% of live ones. Pay special attention to tables with frequent updates and the presence of any long-running queries. A single forgotten query can halt vacuum and balloon a 5 gig table into 50 gigs in hours. If you see a spike, find the open transaction and kill it. So MVCC lets readers and writers coexist peacefully by never overwriting a row. The price is space. Updates and deletes create dead tuples that only vacuum can mop up. A single open snapshot can freeze that cleanup for hours. Indexes add their own layer of dead weight. Master this dance, monitor bloat, tune auto-vacuum, and watch for long-running queries. And you'll get screaming concurrency without the table swelling out of control. Thanks for watching. I hope this one was useful. See you in the next video.